Learn from the original, Tom Henry, the man who has written 23 electrical books, produced 40 electrical videos, recorded 15 electrical audios, prepared over 21,000 electricians for their exam in 15 different states, designed the Learn to Be an Electrician home study course, president of The Informer, the electrician's newsletter, and works part-time giving electrical expert testimony in lawsuits. This video series covers the calculation part of an electrical exam. 8 videos for the journeyman exam, 12 videos cover the calculations for the master exam, the contractor's license. View the video first, then answer the calculation question sheets that came with this video, and I'll personally go over the answers with you. Try and attend a weekend Tom Henry seminar in your area. Prepare yourself properly with Tom Henry. Hello and welcome to my video titled 3-Phase Transformers. Now here comes the big guy for the master. If you're taking the master electrical examination, or if you're taking a state examination, or an electrical exam for the electrical contractor, this is the guy that pulls the permits, then this is an area that's heavily asked. I mean, it's the area they expect you to be knowledgeable of. And even later on in this video, we're going to talk about the impedance and the short circuit calculations and the overall picture. We're going to put this thing together. Now see, the problem with this is the average electrician, the everyday electrician with the tool belt and the conduit bender, this is not his expertise. When I used to have time to tutor here in Orlando, the biggest single call for tutoring was on this subject right here. You see, we teach it in our classes, like in our Tom Henry weekend seminars or evening classes. We go through this. Now, here's the problem with group teaching. When you're teaching a group, you put the information out there. Now, whether they understand it, whether they got it or not, who knows? But see, tutoring, like one-on-one, when I'm tutoring one-on-one, like on this subject here, hey, in an hour, I can turn somebody around in 1 hour of tutoring, one-on-one. That's the easiest teaching there is. Because see, I don't move to the next step until I understand that they understood this step. And once we're focused, we're on the same frequency, like, okay, he understands this step. Then I move up, then I move up, then I move up. But see, in group teaching, you have no idea of if they understood. Now, the advantage of videos is that you can rewind this thing. And here you talk about you talk about an asset. Here's an asset. If I'm going for an exam that asks 3-phase transformer questions, I'll tell you one thing right now. Let's get this understood. You have to go through this book. This book's going to give you all the looks, all the angles. I'm going to talk about it on this video, but it's called More. And you cannot do too much of this, you know. Now, no big words. Like when I was first taught this, it was by an engineer. And they'd use the words like the parallelogram and the hypotenuse and the cosine and the tangents and all the vectors and all the trigonometric functions. So when I first started teaching, you know what I said? I've got to teach at a level that the electrician will understand. And I think that's the biggest key to my success, is I don't use all the big words. Mainly, I don't know how to spell them. So if I make any spelling errors on any of these videos, you understand why. I'm an electrician. I'm not a designer. I'm not an engineer. I don't have any fancy titles. I'm an electrician. But at this electrician's level, what I've done over the years, and this didn't happen overnight. I mean, this took years of listening to you and listening to your questions and the problems and the difficulties and with this subject. So from listening to you and teaching you over the years, I put this into, hopefully for you, a very simple format. I call it 1, 2, 3, 4. A 1, 2, 3, 4, and I'll answer the questions they ask me on an exam. And as we go through here, see, on this book I wrote on transformers, there's several ways you can connect it. You can go delta to delta, Y to Y, Y to delta. Like when we're coming out of Niagara Falls or Hoover Dam or these places in this heavy step-up transformation, yeah, there's all kinds of connections. But what we're focusing on this video is called delta Y. And I've seen this even asked closed book. What's your most popular distribution? Delta Y. See, some areas in the U.S., they don't no longer want a delta highlight. Forget it. We want that Y. And I'll show you on this video why. And this is important. Now, what we had to see, like when you drove down the highway today and you see these poles, and these poles have these wires, on a three-phase system, you're going to see 3 wires. But when we start at that source of energy, that AC generator, we're going to have these 3 single-phase transformers. And each one has 2 wires. Well, that's 6 wires. So what we're going to be doing, we're going to be taking these 6 wires, and we're going to connect them to where we only have 3 wires. And see, when we make these connections, delta to Y, then it's going to change our voltage and current relationships. And I'm going to put this in a little format. You have a sheet 1 that came with this video, or you have the formula insert sheets. Your formula insert sheets, which is an asset, I mean, they're pre-drilled, you can put them in your loose leaf, but it'll have this same format that you have on sheet 1. So if you want to grab your sheet 1 and follow along with me as I do this video. But the starting point, like for me to start, I'm going to come right over here, and we'll call this a delta Y. I mean, this is our format for today. Now, the delta Y, let's start this way. We just completed a video on a single phase transformer. There is a single phase transformer. It has a primary winding and it has a secondary winding. That's single phase. This video, we're talking about 3-phase. So what we're going to be looking at, we're going to be looking at 3 of these single phase transformers. Now, the picture I want you to see the 6 wires? The 6 wires? Now what we're going to be doing is taking these 6 wires and connecting them into 3. Now say over here on this delta, the primary, let's just draw a delta. This is the closed delta. It kind of looks like a triangle, doesn't it? All 3 coils are connected together. The Y, it looks like it sounds. It comes down like this. Now it has right here a neutral. Oh, they can use a big word and say the neutral is symmetrical with all 3 phases. And what that means is it's connected to all 3 phases. But there's your picture of a delta primary with a Y secondary. Now, sometimes on an exam, they'll say to you, well, connect this. Connect these 3 single-phase transformers, delta Y. Well, if you come over here on the primary side to the delta, you see how these coils are hooked together here? They're hooked together here, and they're hooked together here. That's called the closed delta. Well, watch. If I was to connect this, I would take these 2 coils and connect them together. I come up here and I take these 2 coils and I connect them together. Now I have to come from here, up here, and make my connection. Then all I would have to do is come in here with a line wire, come in here with a line wire, and come in here. And I could go L1, L2, L3. That's how my delta would connect. Now if I come over here on the secondary, that's going to be my lower voltage on a step down. See how this looks as Y? Well, it shows the neutral being connected to all three coils. I'm going to start right here at the top. I'm going to bring this wire down, and I'm going to call it my neutral. This will be my neutral. Now for polarity purposes, since I come off the top this winding, I'm going to come right off the top of this winding, make my connection. I'm going to come right off the top of this one, make my connection. All I have to do is go line 1, line 2, line 3. There's my connection for a delta Y. Now the next thing we need to do is give this a voltage. Let's say that this is 480, it's a common, and the secondary is going to be a 208/120 volt. That's a common everyday voltage that you use out on the job. So we're not going to use anything out of the ordinary. Now watch. On the single phase video that we done earlier, we talked about ratios. And see, the important thing about watching this video is the first thing you got to do is understand single phase. So to watch this video without first watching the single phase video is going to make life more difficult. So the first thing you do, once you understand single phase and you understand ratios and volt amps and turns and how all this works, then when we come here and they say to you on an exam, what's the ratio of this transformer? Hey, it sounds like bingo night some nights in class. I get all kinds of numbers. You know what I say in class when I start hollering out all these numbers? I just say this. You're an electrician. And always remember this, even on the examination. Listen, if you're an electrician, you take a meter, right? Your voltmeter. Now watch. If you had your voltmeter and you want to know the ratio of this transformer, this will help you more than anything. Take that voltmeter and come right over here. See where I said the primary is 480 volts? And you put your voltmeter right there. And you know what you're going to read from here to here? You're going to read 480 volts. But you have to note where my fingers are. My fingers are from line to line, like line 1, line 2, line 3. But I'm reading line to line on a delta primary 480 volts. But here's the key. You see what else I'm reading? I'm reading the phase voltage. There's one phase, one coil, one winding. So I'm reading, if I want to take this 480 and place it on this sketch, here's where it would be placed. Right here. It can be right here. It can be right here. That's line to line. What do you mean line to line? Well, here's a line, right? Here's the other line. And it's also reading one phase, one coil, 480. You agree? Now watch. You're the electrician. You take your voltmeter and you walk over to this secondary. And we said the secondary voltage is 208/120. If you took your voltmeter and you put your voltmeter from here to neutral, which one of those two voltages are you going to read? 120. Why? Because you're reading the phase voltage. On this exam, this is so important when you see them type in phase voltage or line voltage. You have to understand what they're talking about. When they say phase voltage, it's one coil. When they say line voltage, I have to reach out from here to here, here to here, here to here, but out there in the line, down here in the phase. See, in single phase, that's where we talked about the catcher's mitt, the transformation depending on the number of turns, coils, windings. We can step voltages up or down here in the phase, the coils. Not out there in the line. That's an entirely different thing in the line. But down here in the phase is where the transformation occurs, the changing of voltages. Now watch. If you say from here to here, it's 120 volts, you're putting your meter right here. 120, 120, 120. See, the 208 volts, that's a line voltage. 208 is from here to here, and from here to here. See, line voltage. You're actually reading across two coils, two phases. Now watch, you come back to the question, they ask you on the exam and they say, what's the ratio? Well, that's easy. 4 to 1. Coil to coil, phase to phase, that's your ratio. You can't believe in my travels how many get that wrong. Oh, they want to take 480 volts and divide it by 208 for a ratio. Wait a minute. 208's a line voltage. It's not a phase voltage. That's out there. We got to stay down here. This is the first thing that you've got to understand. Once we have the ratio correct, then we can walk through our format. But this is also important. It's what I call getting started off on the right foot. Now, if I take this out, we're going to build us a format. And let's start with the Y. And you can help me. You can make your own format like we did on these insert pages or sheet 1. What? You just said a moment ago, if you put a meter right here, this is a Y. A Y. If we put a meter from right here, you said it was 120 volts. And you said if we put a meter from here to here, it was 208 volts. Watch. Our format for a Y is, if I take the phase volts times. Now, here's the only number that I'm going to use. It's the only number I need. I mean, some books you read, they got the 1.14, they got the 866, the 577. I mean, all kinds of numbers. I stick with this number right here, 1.732. And that's all I need. And I'll answer the questions. Well, if I take the phase voltage, watch, which was 120 times this, it's going to equal the line volts. Just try that in your calculator. Take your calculator right now, watch. And let's take 120 times 1.732 equals 207.84. Well, if you wanted to come closer, watch. If I took 3 and hit the square root button and then multiplied that at 120, I got 84609, but whatever. In other words, rounded up, you're going to have 208 volts, the line voltage. Now, here's where that's so important. If I take this same format and just flip it over, example, say I take the line volts and I divide that by the square root of 3. That's going to put me back to phase volts. I mean, if you have your calculator, you say, well, that makes sense. If I take 208 and divide it by 1.732, it gives me the 120 volts. But here's the key to this. Say the day you take the test, they say to you, with a typewriter, oh, the line voltage on a secondary of a Y is 480 volts. And they say, what's the phase voltage? You come right to your format, you take your calculator, watch. Take your calculator right now. Take 480 and divide that by 1.732 equals. Does that number look familiar? 277 volts. That's your line to neutral voltage on a Y, 480 volts, line. See, we don't know which question they're going to ask you, so we have to learn categories. And we do this by making ourselves a format. Once I have the format, then I can answer their questions. Let's come over now and talk about current. In other words, that was the voltage. Let's talk about the current. Let's say in this Y that I have a three-phase 10 amp load. Three-phase 10 amps. Now here's the picture you see. If you have 10 amps in a coil, you get 10 amps going right out that line. 10 amps in a coil, 10 going out. Coil going out. I have a straight flow. So in a Y, my format will be phase amps equal line amps. It's the same guy, the same 10 amps. So there is our little format on a Y that when we connect it, and see that's all this is, a connection. And once we connect it that way, you'll see how the voltage and current relationships do different things. See, I can take 3 doorbell transformers and lay them here on this table, and I can connect them delta Y. And that's all it is. It's just a connection. 3-phase transformers, it's no big monster that's going to eat your toes off. It's a connection. And all they're saying on this exam is once you connect it this way, then how many amps, how many volts? Questions. Let's go over on the primary side for this delta. Let's talk about this delta, or delta format. And you said earlier, if we put a meter right here, we would be reading 480 volts, and that we were reading line to line, and we were also reading one phase. So in a delta, watch, you can say that phase volts equal line volts. It's the same 480. That was easy. Now for the current relationship, let's say with this delta we use the same 3-phase 10 amp load like we did over here. You can see now in a Y how it went out. Well, can you see already what happens with a delta? With a delta now I have 2 coils, 1 line. I have 2 coils, 1 line. 2 coils, 1 line. See, now it's not a straight flow. So what we do in this delta for current, you take the phase amps times the only number that I use, 1.732, the square root of 3. And this will give you line amps. Got one thing left to do in our format. For this delta, all you have to do is flip this over. Just take the line amps, divide that by the same number, the square root of 3, and it'll put you right back to phase amps. Example, say you're taking an exam, and they said, well, if you put an amp clamp right here, you put your old amp clamp right on that wire, what would that amp clamp be reading with a 3-phase 10 amp load? What? You would take the phase amps. See, that 10 is a phase. That's a phase amps. And I want to know lines. See, these are lines. This is coil, phase, line. That's the first thing you have to distinguish. What is a phase? What is a line when you see it in a sketch or in a typed question? When I put my amp clamp on the line, I want to know line amps. That's what they're asking me. What's the line amps, not the phase amps? If it's a delta, I come right here and I say, well, the phase amps are 10. I'm going to multiply it. I'm going to have 17.32. That's what my meter is going to read. That's going to be my line current. Over here, if I put an amp clamp there, it's going to read the same as a coil, 10. Over here, it's 17.32 amps. That's our picture. That's our format that you have on sheet 1. In your loose leaf code book, the one with the rings, and snap in your formula inserts, and you'll have that right with you as you prepare for this exam. Now what I'm going to do now, I'm going to put this into a picture that you have to see. Let's make this delta. I'm making a Y. I'm on a secondary. I need the primary first, don't I? Let's make this delta, which is a triangle, a Greek word. We make this delta primary. Here comes our line wires. They come over here for the Y, the secondary. Now see, that was the same 3 single-phase transformers that I had on the board earlier. When I drew them like this, and we connected the 6 wires in the 3. Same guy, you're just looking at it at a different angle. Like this coil's looking at this one, this coil's looking at this one, this coil's looking at this one. We're just showing it in a different perspective. Now, here's what you need to know. There's 4 reference points. Now this is my 1, 2, 3, 4. I'll answer the questions they ask me. But see, you have to understand when they take a typewriter, when they talk about the secondary line, you have to see it here. You have to say, where is the secondary line? Now watch. Right here was what I call position 1. So I come right over here and I say, that's the secondary line. Position 2, see right here, is what we call the secondary phase. Our third reference point, right here, is called the primary phase. And the last one, number 4, is called the primary line. Now see, they can take a typewriter, text, and ask you a question. And on all the videos that I've tried to walk you through, what did I say? Sometimes when you read text, you get all confused. I keep saying and harping in all these videos and the books that I write is, try to take those words, those sentences, those phrases, and put them into a picture, a sketch, if you can. Example, the day you go, say they take a typewriter and they say, well, a 3-phase 480 / 208 / 120 volt transformer. Has a secondary line current of, this numbers, you pick any number you want, say 200 amps. In other words, they're making a statement. Then they come back and they say, what is the primary line current? That'll be our question. Well, after reading that question, what? And they'll give you multiple choices. You have 4 choices of answers, A, B, C, D. But here's what you do when you see a question in text like that. Make yourself this picture. Then you come back to the question. In other words, they're saying 480, 208, 120. We just learned a moment ago that the ratio is 480 to 120 volts. That's called phase to phase. So right up here, I'm going to right now write the ratio 4 to 1. Okay? And we learn how we determine that. Now, you read on, this says, excuse me, that you have a secondary line current of 200 amps. In other words, they're telling you you have 200 amps. What you do, you take your pencil the day of the exam, and you come right up here, and you put 200 amps. Why? Because the secondary line is right here, position 1. So you go right up here at position 1 and write in, just pencil in 200 amps. Now, with your format that came with sheet 1, watch. Go to your format. Is this a delta or Y? It's a Y. So you go to your format for a Y. What does it say on a Y that the line amps and the phase amps? Does it say same? Yes. So what you would do, just pencil in. This 200 amps is going to come right down here, and it's going to wind up at position 2. You have the same 200 amps at position 2. Now, here's where it's important when we go from 2 to 3. Step 2 to 3. This is where the ratio becomes involved. Now, over there on that delta primary, I raised the voltage to 480. See, over here, in this coil, I only have 120 volts. I raised the voltage 4 times. What's going to happen to the current? I mean, we learned this in single-phase transformation. When we raise the current, what happened to the amperage? It went down. Well, if I raise the voltage 4 times, up to 480, what's going to happen to this guy? It's going to become 50. 50 amps in the primary phase. Now, the question was the primary line current. Well, position 4 right here is our primary line. Now what I have to do, I've got to get from 3 to 4. You go back to your format, your sheet 1 format, and you say to yourself, is this a Y or is this a delta? It's a delta. And when you come to your delta format for amperage, it said phase amps times 1.732 line amps. See, this is line, this is phase. I've got to get from phase to line, so I would have to take this 50 amps times the square root of 3. Like punch that in your calculator. You should be looking at 86.6 amps. 86.6. That would be the answer to this question. And it's called 1, 2, 3, 4. There are no shortcuts. 1, 2, 3, 4. All you're saying to yourself as you go through this, are we talking about a Y? Are we talking about a delta? You go to your format, you take your calculator. Is it the math? No. What it is as you read the question, you have to see where the numbers go in this 1, 2, 3, 4 sketch. See, the day you go to take a test, they may ask you, or they may tell you, hey, you got a primary phase of 50 amps. What's the secondary phase? 200? Done. The day you go, maybe they take the typewriter and they say, on the secondary phase, you got 200 amps. What's the secondary line current? Same. Or the day you go, they may say, the primary phase has 50. What's the primary line? 86.6. In other words, you could take any number. Any number. Watch. If I erase these numbers, watch. You could take any number you want, put it at any one of those 4 positions, and I'll tell you the other 3 numbers, like that. Take any one number, you can put it here, put it here, put it here, put it here, I don't care. Wherever you put your number, whatever your number may be, if I follow this format, I can tell you the answer of the other 3 points just by following what I have on the board. And that's all I want you to do on this test. As you read the question, I want you to be able to take that number. Example, say they put a number here, 200 amp. In other words, they retype this. And they say, you have a primary line current of 200. What's the secondary line current? Well, here's the secondary line, position 1. See that question? I put the number in the sketch, and I put the question mark. They gave me this, and this is what they want to know. By following this sketch, what's the beauty of it? Is this a delta or a Y? It's a delta. I go to my format for delta. Watch. This is the line. The first thing I got to know is the phase. I got to go from line down to phase in a delta. We learned earlier that we would have to take on a delta, watch, if I wanted to know delta phase amps, in other words, this is what I want to know, phase amps. I would have to take the line amps, this is what your format says, and I would divide that by the square root of 3. So if I took 200 amp and I divided it, you should be looking at 115 approximately amps. So you come over here right now and you write down 115 amps. Now do you see that ratio? What's going to happen to this if I lower the voltage 4 times? This is going to go up 4 times to what? 460? At position 2, I have 460 amps. This is a Y. And if I go to my format for Y on sheet 1, what does it say about phase amps and line amps? What have we learned? They're the same. Same guy. This answer is 460 amps. You can practice this. You can take any number. Let's say you could take 115 and put it here. You can go this way. You can go this way. I could answer that question. I could answer it on an exam in 4 seconds. I could. All I would have to do is take this calculator, and I would take 200 divided by 1.732 equals times 4 out the door. 461.8 amps to be exact. 1, 2, 3, 4 out the door. You know, it's like, what else do you want me to do? You can take an extremely cumbersome, difficult exam question, massage it, get rid of all the big words and all the fancy numbers, throw all that stuff out the window, take your voltmeter in your mind with your calculator, make a simple sketch, put it into a format, and I'll answer their questions. That's what we're doing on this video. I have several sheets that come with it. I'm going to have you work. But again, get in a quiet corner and go through that book. See, I can look at numbers. Once you go through that book, you'll learn the same thing. I can look at numbers and tell you how a transformer is connected. Watch. If you said to me, it's 480, 277. You know what I say? That's Y connected. If you said to me, it's 208 volt / 120 volt, you know what I say? That's Y connected. How would you know? Because on a Y, the lower voltage will not divide into the higher voltage evenly. Will not. If you said to me something was 460/230, you know what I say? That's a delta. If you want to talk about your 240/120, you know what I say? That's a delta. On a delta, the lower voltage will divide into the higher voltage evenly. So I can just look at numbers. I'm going to show you on this video some other little tips, things to do. I'll show you where the questions come from. Example. Say you have a delta secondary. And I mentioned earlier, some places today don't want it. But you know as well as I do, you have it in areas throughout the United States. Well, here's our delta secondary. Now, when you say secondary, look, it's going to have a neutral. And here comes your wires, your line wires. Well, see up here is what they call the high leg. Oh, it's referenced 3 places in the code book. It says it should be tagged or identified orange in color. A lot of utility companies want it as the center, B in your panel board. That's up to the utility company, their designation. But the code book says, hey, it's got to be identified, and here's why. Sometimes you'll hear it called the wild leg, generally the high leg, because here's what's happening. See, if you gave us a voltage, let's give it a voltage. Let's say it's 230/115. Well, here comes your voltmeter again, and I want you to keep in your mind the day of the test. If you put your voltmeter from line to line, you've got to read 230. And if you put your voltmeter from here to here, you're going to read 115 volts. Or if you went from here to here with your voltmeter, you're going to read 115 volts. Because see what you're reading, this 115, you're reading what we call half of a phase. Your phase voltage is 230. The 115 is half of a phase. They take what they call a midpoint tap, a center tap. Now here's what they ask sometimes on an exam. Oh, they'll say, well, what if we put a meter from this point up to this high leg? I'll extend this wire out. If I put a meter between these 2 points, and they'll go, well, what would the volts be? They'll ask you a question. Well, the picture you want to see is you're no longer reading one phase, and you're no longer reading a half a phase. From this point neutral to this high leg, look what you're doing. You're actually coming across a half a winding and a full winding. Now here's how you would answer this. Don't jump on choice A, because it'll be 208 volts. You don't memorize 208 volts. If you want to memorize something for an exam, memorize this. Always take your lowest voltage times the only number that I ever use. And you'd read 199 volts. And see, the reason they do this, if this was 240, 120, if it was, then if you took 120, your lower voltage, at the square root of 3, there's your 208 volts. So sometimes, intentionally, they don't make it 120, 240. They'll make it 230, 115, or 220, 110. Because when you change voltages, this voltage changes. So there is no memorizing 208. What you memorize is the lower voltage at the square root of 3. Then you'll be okay. Sometimes I've seen them ask this: how many lines could you connect to neutral? 2, not 3, 2. But by putting it into a sketch, now I can see all this stuff that they're asking me. That's what we call the delta secondary with the highlights. If asked, you know, I have to cover all these things. I don't know the day you go, what category. I try to teach all the categories so that when you go, there are no trick questions. I always like it when a guy says, I had a trick question. Well, a trick question is it's one that you've never seen or had explained to you. That's the only trick to it. Now I'm going to talk about open delta. See, say we had this delta transformer, and let's say it's 10 kVA, just to have numbers. And that's kind of like, you ever hear the old phrase, you put all your eggs in one basket? So you can take 3 coils, put them all in one transformer, or you can set 3 single transformers. See, in the industry, it's best to set 3 single transformers. That way, if one would burn out, hey, if I would lose one of these, watch. Say this guy burns out, that's called an open delta. Or some small machine shops and stuff like that, they actually start up open delta. Then as the years go by and they get more money in their pocket, they add that 3rd transformer. See, you can run this 3-phase with 2 transformers. Now you're going to sacrifice. Here's how you sacrifice. Your number that I use is the square root of 3. If you would divide that by 3, you're going to come up with this 577. I mean, that's the magic number for this stuff. If you would take this times 57.7%, you could operate open delta at 5.77 kVA. Just a little over half. In other words, I can still keep the lights burning, but I'm only going to have about half the power. But I'll still have my 3-phase system. Now that's a question that's frequently asked on a master examination, transformers. I've tried to touch on, and I'm going to later on, I'm going to put more stuff on here where I'll show you some more tips and things to do on questions from this area. See, my job is to prepare you for this examination. And again, I'll say it one more time. This has been the most troublesome calculation for a master exam, 3-phase transformers. So I've tried to show you. Now I think it's best if you do this. If you take what I've asked you, showed you, told you to do. When I say ask, I mean turn on the calculator and follow along with me. I can't make you. Now this sheet 1, sheet 2, the first sheet that you have with questions, sheet 2, now listen, it's closed book questions in this category, 3-phase transformers, closed book. So when you work sheet 2, no books. As I explained on an earlier video on this exam, when you get the closed book, it's what you have on the disk. It's what you've learned, it's what you've stored, it's what you've retained. So as you read these, I say closed book, you read them carefully. I mean, we don't want to miss them. Read them carefully. If you can put them into a sketch or something with a pencil, do it. But I want to have you now shut off your video and go to sheet 2 and just answer those closed book. And when you're done, turn it back on, and I'll be right here, and I'll show you some different things. Okay, the answer to number 1 on sheet 2 is A, equal to the secondary phase current. Because see, you have a 480 primary, that's delta. The secondary is a 208 120. Y. You go to your format for a Y for amps. Remember, phase amps, equal line amps. Now in question 2, watch. In question 2, you have a 480 volt, 208, 120 volt. So they say it's a delta. Why? So far, so good? I mean, the Y is over here at 208, 120. Now watch. Here comes the question. And I have so many people in class miss this. And it's kind of like the day of the test, you got to talk to yourself and do what I'm doing right here. Identify the voltages, which one's delta, which one's Y. Then look at the question. The secondary line voltage, what's the secondary line voltage? 208. Did you agree? The secondary line voltage is 208. Now watch. Is blank secondary? Now you come to question, choice A on number 2. Here's choice A. Is 208 less than the phase voltage 120? Because see, this is the phase, this is line, and this is phase. So when you go to choice A, you say, is the secondary line 208 less than the 120? No. 208 is greater than 120. You come to choice B. Is 208 equal to 120? No, it's more. You come to choice C. The correct answer. 208 is greater than 120. See what we're doing? You've got to talk to yourself. Number 3, I mentioned this earlier on the video. How many wires can use a common neutral? 2. The most common 3-phase connection, delta Y. That's what this video is on. Number 5, here's one I see missed. Number 5. I can sketch it out for you. Watch. Here's my primary windings. I come over here to the secondary. What? What's this called? Delta delta, I think. Yeah, it's a 480, 240, 120 volt. That'd be a delta delta. Why? 240, 120, that's a delta. 3 phase. What they're going to do, they're going to come over here and they're going to tap one of these phases with a neutral. You know what the voltage is going to be here? 120 to here. And from here it's going to be 120. That's at half a phase. But what's the phase voltage? 240. Phase voltage, remember? You're going to come back with a correct answer of a 2-to-1 ratio. The 120 is not a phase voltage. Your phase voltage is 240 volts on all of this. Okay. And your phase voltage over here is 480. Sketch it out, connect it. See, that neutral is half a phase. And number 6, the last one, power in either single phase AC or DC is always equal to C. It's called I squared R. That's your power. When you get into that cosine stuff, then you're talking about phase angles, 3-phase. I'm going to have you stop your video, and I'm going to ask you, now we're going to go into calculations on sheet 3. Now there's 6 calculation questions with multiple choice. Don't work sheet 4 yet. I want you to work sheet 3 only. Because see, once I go over this, then it'll help you towards sheet 4. So work sheet 3. When you got them, turn your video back on. In question 1, the answer is 50 amps. It's called the unbalanced Y on a neutral. What I would recommend on this reminders book, which is pre-drilled to fit in your loose leaf, on page 50, there's a formula showing you how to calculate. But what you're doing, you're taking the largest load, and the neutral would have to carry that maximum current, 50. See, in question 2, it's the same type question that you have here. If I put question 2 on the board, it's going to look like this. It's at Y, and it's going to have 8,000 and 8,000 and 8,000. And if you use that formula, all you'd be doing is this. And in question 2, you'd be coming up with a maximum unbalanced, and their answer is going to be 67 rounded up. So same type of question, 1 and 2. Now number 3, if the watt meter reads. Let me put number 3 up here, and I'll show you how to solve it. They're looking for current. So I want to take the 15,000 watts, and I'm going to divide that by several things. 208 volt, it's 3-phase, and they're saying it has a power factor of 0.96. And if I run that through my calculator, I'm going to come up with 43.37 amps as the answer. That's the current flow. Now, to work along with you, take your calculator. And I've done this on other videos, but I'll do it again. Take your calculator, put it on 0. Now press 15,000. Now, I want to hit the divide button. Press 208. Now here comes the important thing. Hit the divide button. Press 1.732. Hit the divide button. Press 0.96. Press equals 43.37. And see, instead of multiplying, I'm dividing, because I'm dividing what's stored in this calculator. I can't write it that way. But see, you would have to take this, times this, then you would have to write this number down, take this number, divide it into there, and you come out with the same answer. What I call everything below this line, I call them bottom line dividers. Just whatever's below the line, divide, 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 equals. I'm dividing what's in the calculator. It's not for speed, it's for accuracy. Because see, every time that you have to come back and put something back in the calculator, then you're more apt, or could be susceptible, to making an error. And so the less movements of the hand with the calculator, I always say the better for accuracy. So that's how I do it. I don't really care how you do it, as long as you get the correct answer. That's what we're here for, is selecting the correct answer. Now number 4 talks about a watt meter reads. Same type question. In number 4, if I would take 12,970 watts. Now see, instead of using 208 and the square root, I'm going to round it out so I can come closer. The voltage is 207.84 volts times, here's my square root of 3, but I'm going to carry it all the way out in my calculator just to have some fun, to show you, times 36 amps equals. It's pretty close enough to call it unity, the correct answer. See, as we talked about earlier, when watts equal voltamps, that's when everything's perfect. That's when you're in phase, right on the money. It's called unity. Number 5. We've got 3 10 kVA single phase transformers. Well, if I had 3 10 kVA, that'd be a total of 30. And if I divide that by 480 volts at the square root of 3, run that in your calculator, 2 bottom line dividers, what is the primary line current? 36 amps. These are the questions they ask. Number 6, they're going to ask you the primary line current. Remember, that was step 4. If this is the delta, remember our format, delta, and this was our Y, what? And they say this is 480. This is that number thing we were doing. And this is 208, 120 volt. a Y. And they say what? The secondary line. Amps, secondary amps in the line. Here comes my numbers. I'm going to put 80. Remember our 1, 2, 3, 4? This is it. They're asking for primary line. We said this was a Y. The current's going to be the same at position 2, the phase. You said earlier that the ratio is 4 to 1. What's going to happen to that 80 amps? It's going to become 20 here. They want to know this guy. This is a delta. We take our format for delta phase at 20. I would have to multiply it, and I would get up to 3464 for the delta line amps. And that's what they asked me right here, 34.64. But see, that's how you could use their sketch. They have a sketch in question 6. You just put your numbers. Put in your 80, your 20, boom. I think if you drill on this and work hard at it, do several of them, then it'll be a much easier calculation. I'm going to have you stop your video. You got one more sheet to go, sheet 4. And let's keep all these thoughts in mind, and let's score real high on the 5 questions, sheet 4. Now on sheet 4, the answer to number 1 is D, 125 amps. That's the secondary line current. And what you would do in question 1 is take the 45,000 volt amp and divide that by the line voltage at the square root of 3. And you're looking at 124.9. Now sometimes someone taking an exam, they get confused. They say, well, I didn't know whether to use 208 or 120. Well, always remember on 3-phase, use your higher, your line. But even then, if you want to do it with phase, a phase is a third of that, 15,000. And if you take it at 120 volts, remember we said on a Y, it's going to be the same current. So you can work it either way. Or you can even do it as a checkpoint that way. In question 2, you have 3 10 kVA single phase. The primary voltage is 40. What's the primary phase? Phase. Well, see, it's a delta Y. So you're talking about this delta. Watch. And it has 10 kVA, 10 kVA, 10 kVA. But see, they're going to talk about a phase. A phase. If they talk about line, I'd take 30,000. But on a phase, I would take 10,000. What's the phase voltage? Same as a line. It's a delta, 480. Phase. These are your key words. Phase. Because they want to know phase amps. 21. 21 is the correct answer, number 2. Now the next 3 questions refer to this drawing. Kind of neat. It's a delta. I have yet myself. I haven't seen everything, but I haven't seen a delta yet at 208 volts. But I don't write these exams. But it's just numbers. So all I have to do is answer their question. In question 3. They're saying I line. That's what that L is for, is line. Well, if you want to know amps, amps is what? E divided by R. So you come over here and you take 208 volt, and they're saying it's 30 ohm. So if you want to know the amps, it's 6.93, which is choice A. But see, this is phase. This is the phase voltage and the phase resistance. And they want to know line in a delta. So I would have to take the phase amps in a delta at 0.1732. In the line current, the correct answer to number 3 is 12 amps. This is your line amps delta. And see, that one's easy to miss. Number 4, the power, that's watts. Watts is E times I, that's the easiest. So I merely take 208 volt at the amperage we just calculated, and you're going to be looking at 1441 watts is the answer to number 4. 5 amps phase, amps phase. Amps is ER 208 30 ohm phase amps, remember? Phase 693. So those are some calculations from 3-phase transformers. Here's more, which I recommend. Here's more. I tried to show in the book, all of them I've seen, but numbers change, but categories don't. See, what you're doing, sometimes in a class, I'm teaching, somebody will ask a question and something hits my mind. They're called spin-offs, and all at once I'll fill the board full of numbers. And oh, there's questions they've asked for 30 years. We had a video on motors. And I said, well, for 3-phase, you'd have to go to this table, 430, 150, for the FLC, the full load current. Well, they've asked this for 30 years. If you had a 208 volt, 3-phase, 10 horsepower, and they'd say, well, what's the VA? And I said on that video earlier on motors, I'd say right there is a good place to write 3-phase volt amps. You'd go E times I at the square root of 3. And I even said right here is what a lot of people forget when they talk about 3-phase. They forget that square root of 3. But see, I've done this long enough. I know if I go to this table for 10 horsepower, 208, this guy is going to be 30.8 amps. And this guy is 208 volts. And if I take these at the square root of 3, this is a question they've asked for 30 years. Here's the answer. 11,000 rounded up 96 volt amps. 11,096. I got it filed right here. But see, watch. If you wanted to turn that into what we've been talking about on this video, let's say this motor, if we could see inside of it. You see this voltage? That's a Y. 208, that's a Y. So if I could look inside this motor, I would see these windings, and they'd look like a Y. And those 3 wires would come out, and I'd make my connections to make that motor run. Now watch. If I put my amp clamp on that line wire, it's going to read fully loaded 30.8. But since this is a Y, you remember we said in our format, like on sheet 1, we said for a Y that phase amps equal line amps. What's the beauty of this? If you took this 11,096, which is the total, and you divided it by 3 phases, you would get round up a 3699 volt amp. And if you took the 3699 and put it here, and here, and here, at each coil. In other words, I just split the 11,000 3 ways because there's 3 transformers, 3 coils. Watch what happens. If you would take this number right here, and we said in our format, sheet 1, if we had 208 volts in the line, how many volts would we have in a phase? Remember our meter? 120. Well, if I took and divided this by 120 volt, guess what? 30.8. Right here. 30.8, 30.8. It's a Y. Coil phase amps is the same as line amps. So some of this stuff, even though it's a transformer, you can flip it right into a motor sketch and do something like that. I always say this on these, it's numbers. Once you have the format, once you learn it, you'll never forget it. See, I get to teach this all the time. I don't need notes. I get it stored. I've done it so many times. And what we're talking about is, let's say you have a delta secondary. Or you could have a Y secondary. The delta secondary, remember the delta is the triangle, and the Y, and since they're secondaries, we'll put a neutral on them. Now in the balancing, here's a picture you want to see, like for balancing things. Say, we call this transformer A, B, C, A, B, C. What you're used to as an electrician, if you're like I was, you're used to in that panel board. You're skinning that wire and you're making that connection to phase A, B, C, those bus bars. But you don't have this picture in your mind of that transformer out there. We're used to the panel, A, B, C. And the picture you want to see for this exam is that transformer, of how this A, B, C in this load center looks out there, A, B, C. And this is what I'm going to show you. Now watch the difference. If you took, say, in your panel board, let's say this is A, B, C. We're over here on the Y, we have a panel board A, B, C. This is our panel board. This is our transformer. Let's say we took a load, let's say it's 6,000 watts, single phase. Okay. If I'm in my panel board, it's single phase, say 240 volts. We'll say this is 240, 120. We'll say this guy's 208, 120. Well, for me to hook this up, I would have to connect that 6,000 from here, from A to B, it's single phase, or I could go from B to C, or I could go from A to C. You agree? Same way over here, to connect it in the panel board. But here's what you want to see when you have to balance loads. Say you're a designer or you're a contractor, and they ask you this on an exam. When you connect this, watch. You're going to take this 6,000 and you're looking for 240 volts. Well, here's 240 volts, here's 240 volts, and here's 240 volts. So wherever I connect that, say I go from here to here. The point I'm trying to make is that 6,000 watt load is on transformer A. It is not on B and it is not on C, because that transformer A is giving me the 240 volts. But if I took this same load and went over here and say this is 208 volts, a higher voltage, and I come over here on a Y secondary and I'm going to connect this 6,000 watts at 208 volts. I can't put it here, I can't put it here, I can't put it here. I either have to go from here to here, from here to here, or from here to here. To get 208, it's a line voltage. That 6,000 would have to look like that if I went from A to C. Way that looks, watch. On A, I would be showing half of that, 3,000. Nothing on B, and C would be picking up half of that. Can you see with that same load, whether it's connected delta secondary or Y secondary, you have to see where the load goes on the transformer that it's connected to, or to. See, if you come along and you said, well, let's do it this way. Let's take out this guy, and let's say, oh, you can use any number. Let's say we have 3 10 amp 120 volt loads. Now here comes the beauty of a Y. This is why they said earlier, what's the most popular connection, delta or Y? Excuse me, delta Y is the most popular, not delta delta or Y to delta. That delta Y is the most popular. A Y secondary, why? Well, see, with these 120 volt loads, I can come from C, put 10 amps. I can come from B to neutral, 10 amps. I can come from A to neutral, 10 amps. But watch, when I come over here with these same 3 loads, I have to come 10 amp, 10 amp, 10 amp. But all 3 loads are on transformer C. Transformer C is the only one that has a neutral conductor. See, when you drive down the highway and you see a pole, 3-phase, and say it has 3 transformers the same size, that's Y connected, because I can balance my transformers. But when I drive down the highway and I see 2 the same size and 1 that's bigger, that's transformer C, that's delta connected. Transformer C has to carry 1/3 of all the 3-phase loads. But it also has to carry all the lighting and receptacles, 120 volts. Where on a Y, your 120 volt loads can be balanced between each phase. That's the difference. I want to show you a question that comes from impedance, short circuit calculations. So what I'm going to do, I'm going to clear the board. If you'll give me a minute, I'll come right back and I'll have this on the board and we'll talk about master type short circuit calculations on transformers. Now on a master's exam, they've asked you to calculate the available short circuit current. And I put on the board that a transformer with a 5% impedance. Well, see, impedance is the total opposition to the flow of AC current. That's not only the resistance, that's the inductive reactance, the capacitive reactance, and so on. Well, it's a very simple calculation if you let me walk you through it. And I'm moving out of the way so you can read it. It'll say the primary, if I apply 5% of the voltage to the primary, will cause the rated load current to flow in the secondary. So 100% of its voltage will cause 20 times. So all you're doing on these calculations is taking the 100% and dividing it by whatever the impedance is. And that'll tell you in this case you would have 20 times the short circuit current, which is the stuff that blows the panel boards off the wall and warps the bus bars. Let me clear this and I'll give you an example. Let's say we have a 100 kVA single phase. Let's say I got 100 kVA single phase, 240 volts, and let's give it an impedance. It'll be on the nameplate of 2.5%. Now what you want to do, you want to find the rated current first. Well, if I would take the 100 kVA, that's 100,000 volt amps. Divide that by the voltage single phase at 240 volts. Round it up, you should be looking at about 417 amps. Now, what you would do at this point, once you have the rated current, take that 100% that we did a moment ago and divide that by whatever impedance they give you. Here they're saying it's 2.5%. Now what happens is, this is going to come out to 40 times. In other words, as that impedance went down, like say it was 5%, now it's 2.5 on this transformer, then the available current is going to be higher. Before it was 20 times, now it's 40 times. So you take your rated current times 40. And the available short circuit here is like 16,680 amps. See, this thing increased 40 times. This increased 40 times up to over 16,000 amps. Now give me a moment, I'm going to clear the board and I want to put a question on that's floating around right now on the examination. Now I have on the board behind me a question on the master's exam from this category that we just discussed. They're saying that calculate the maximum fault current available at the secondary terminals, 750 kVA, 3-phase, 240 volt, that has a 5.5% impedance. They give you 4 choices to choose from. Now the first thing I want you to do is find the rated current. Like you would take this 750 as 750,000 VA. See, K meaning kilo. It's at 240 volt at the square root of 3. And as I've said before on these videos, just take your calculator, clear it, get it on 0. 750,000 divided by 240, hit the divide button, 1.732 equals 1804 is what we call your rated amps. That's where you start. Now, all you have to do when they give you an impedance, whatever that impedance is, just divide it into 100. Just take the 5.5, the impedance, divide it into the 100. What's the 100? The 100%. Remember, we had it on earlier. This comes out to 18.18 times. In other words, at that impedance, this is going to be 18 times higher. All I do now, I come over here and multiply this by the 18.18, and you're going to come up with 32,800, which is going to be choice B. Now, what I've tried to do on this video, which, as I say, you can rewind it, I've tried to take you a walk through the questions that's being asked today. I'm going to sum up this video. I kind of have a little Nikola Tesla in me. So as we talked about single phase and 3-phase, and I took you to the power plant and down the highway of electricity, I want to talk a little more about this electrostatic field. And I'll show some more on later videos, probably the last video. But I want to show you what an electrostatic field can do. I can actually light a fluorescent light in this room. So I'm going to show you, and this is from my Learn to Be an Electrician program, is I try to take a guy and teach him how to be an electrician by showing him things that a lot of times he may never see in his daily travels. I guess I should have titled it Learn to Be a Better Electrician, because a lot of the electricians today are signing up for the program because what? They want more education. But let's take a look at this film clip. Here's a picture that's on the wall in my office. This was a Pulitzer Prize award-winning photograph. This young man actually got hit with a high voltage, and luckily his friend was on the pole that gave him mouth-to-mouth resuscitation. This picture was called The Kiss of Life.
And see, when working with these higher voltages, as you can see, extreme caution is used in safety. And around these towers, sometimes I've read articles and there's been lawsuits where when you push this voltage up so high, and it's out there, what we call the skin effect. This AC, the electrons are flowing out there on the skin, and it makes this magnetic field. And they've had people say, man, my house is close to this tower, and it's ruining my television reception, and it's doing this, and it's doing that. And it's called an electromagnetic interference that surrounds some of these conductors when you're at extremely high voltages. So a lot of engineering and designing goes in this utility to get it to the service. I want to show you a demonstration now on the Tesla coil. Let's take a look at it. Now in energy, we talked about Nikola Tesla. Here's an example of a Tesla coil that we put together, sitting on an old milk crate. But inside that milk crate, we took a sine transformer, about 5,000 volts, and we took this 5,000 volts and put it in parallel with a capacitor made out of aluminum foil, and we put the primary and the secondary there, and you see up the top, there's two balls like, or the electrodes. And what we're going to do in this demonstration, we're going to show you how to take voltages and step them up like they do on these towers to an extremely high voltage. And I'm going to show you what happens in the electromagnetic interference. I mean, I'm even going to show you how to light a fluorescent tube just by holding it in the field of this coil. How's that for an exciting demonstration of high voltage? I've been told that to jump an arc in a dry humidity 1 inch, it takes 80,000 volts. And we were approximately 6 inches, so we're over 400,000 volts you see on those electrodes at the top. But did you see how I can take that fluorescent 40-watt fluorescent bulb, that tube, and wherever I move it in that electromagnetic field, did you see that tube light? It's amazing, isn't it? Nikola Tesla, this was back in the 1800s when he done these experiments. If you ever get a chance to read about Nikola Tesla, get that book. In our bookstore, we have one called Nikola Tesla, The Man Out of Time. It's the only book I've ever had that once I started reading it, I couldn't lay it down. A very exciting individual with the AC alternating current and the higher voltages.
Well, this concludes our video on three-phase transformers. I hope you've enjoyed the educational trip. And if you're out there working with a training program or training someone working for you involved in education, I wish you'd take a look at my Learn to Be an Electrician program, which I've tried to take the guy from the beginning and all the way through the industry. And from the book that I've written on electrical history, I've tried to open these pages and introduce them to guys like Tesla and the people that have made our alternating current system what it is today. I'm going to close now, and I'll see you on the next video. I would like for you to meet the people responsible for our success. My wife, Crispina, the director of videos and computer animation, a very talented self-taught person. We met in Hong Kong. If you call Code Electrical, it's a good possibility you'll be talking to Mary. 11 years with the company. Mary hails from Wisconsin. Bob's a very good salesperson, as he can answer the questions you have on our materials, purchase orders, accounts payable, etc. Bill is my first employee I hired over 11 years ago. He is in charge of the shipping department. Bill, Bob, and I grew up together in Ohio. Nellie, our newest employee with 3 years, is the wife of Jim. Nellie is our doer. She gets it done. She hails from the Philippines. Jim and I met at Disney in 1981. He was the chief electrical inspector. He teaches throughout the U.S. and is the director of our Learn to Be an Electrician program. My son Tim runs Code Electrical classes. As you can see, Tim even runs Model T Fords. He keeps busy running the company, teaching classes throughout the United States, and keeping them Model Ts running. If you're visiting the Orlando area, stop by our facilities. It's called the Electrician's Bookstore. Just say hello. You see, we're very proud to be a part of the electrical industry. Check out our internet site. It was designed by my wife and director, Crispina.